precision are two important terms. For example, if 5 darts are thrown and all hit the bullseye, each throw is said to be accurate and precise. Accuracy is the degree of closeness of the measured value to the true or actual value. How close the darts land to the center of the bull's eye determines the accuracy of the throw. Precision is the degree of resolution of a measured value when the same quantity is measured with different devices. If all 5 darts land at the same point, then the throws are said to be precise. Take, for example, an object whose absolute length is 32.56 mm is measured using 2 different instruments. Using the first instrument with a resolution of 1 mm, we obtain the measurement as 32 mm. Let us call this measurement M1. Using the second instrument with a resolution of 0.1 mm, we obtain the measured value as 32.5 mm. Let us call this M2. Here, M2 is more accurate as it is closer to the object's true value than M1. Also, M2 is more precise as the resolution of the instrument used is greater than that of the first one. Any quantity that is measured should be accurate and precise, especially in science and technology. In reality, however, measured values carry uncertainty. This uncertainty is called an error. Errors are classified as systematic errors and random errors. A systematic error is a unidirectional error. That is, it is either positive or negative. A systematic error can occur due to an imperfect instrument, a faulty measurement technique, or incorrect process of measurement. Errors may occur due to the use of an imperfect instrument for measurement. Such errors are known as instrumental error. For example, if the needle of a simple balance is skewed or bent, it always shows a weight that is more or less than the actual weight of the object being weighed. Errors may occur due to an imperfection in an experimental technique or procedure adopted while measuring. For example, keeping a thermometer under the armpit will not measure the body's exact temperature as the mercury bulb is exposed to external factors such as air in the room, humidity, etc. Errors may also occur due to an incorrect technique or procedure being followed while measuring values. Such errors are called personal errors. Parallax is one such error. While measuring the length of a line using a foot scale, if you tilt your head, the length measured will be shorter or longer by a millimeter or 2. Systematic errors can be minimized or eliminated by using a perfect measuring instrument and by improving the technique or procedure of measurement. Random errors are akin to what they are called random. These errors vary in terms of sign and size. That is, they can be either negative or positive, and the quantum of error varies in absolute terms. These errors can arise out of unpredictable situations. such as a sudden change in environmental conditions, voltage fluctuations, or mechanical vibrations in the experimental setup, etc. Random errors can be minimized or eliminated by ensuring that measurements are taken under stable conditions and using properly set up instruments. Another type of error is least count error. This can be associated with both systematic and random errors. Least count is the smallest value of measurement that can be measured using an instrument. All values are considered precise up to the least count of a measuring instrument. For example, if you are using a meter scale, its least count is 1 millimeter. Hence, any measurement error will be in multiples of millimeters, not less. In academic laboratories, the general equipment used to measure length is a Vernier calipers and a screw gauge. The least count error in a Vernier calipers is 0.01 centimeter and for a screw gauge is 0.001 centimeter. Least count error can be minimized or eliminated by using high precision instruments or improving experimental techniques. Another way to reduce such errors is to repeat the measurements and take the arithmetic mean to bring the measured value closer to the actual one. If n measurements are taken, say A1, A2, A3, A4, so on till An, then the final value will be taken as the arithmetic mean of these n measurements. In the absence of a true value of measurement, this arithmetic mean is treated as the true value. The magnitude of difference between the true value and each measured value of a quantity is called the absolute error of that measurement. It is denoted by mod delta A. Since an arithmetic mean is considered the true value, delta A1 is equal to A1 minus A mean. Delta A2 is equal to A2 minus A mean, and so on till delta An is equal to An minus A mean. Individual error, delta A, may be positive or negative. However, absolute error, mod delta A, is always positive. Mean absolute error is the arithmetic mean of absolute errors of all measurements. If we take a single measurement instead of n number of measurements, then the value of the measurement lies in the range A mean plus or minus delta A mean. This implies that any measurement of a physical quantity A is likely to lie between the values A mean minus delta A mean and A mean plus delta A mean. Instead of absolute error, we often use relative error. Relative error is the ratio of mean absolute error to mean value of the measurements. Relative error is denoted by delta A. When relative error is taken in terms of percentage, it is called percentage error. When a quantity is derived from more than one measured value, the error in the derived quantity may be a combination of errors in the values from which it is derived. For example, the volume of a cuboid is the product of its length, breadth, and height. If there is an error in measurement in length, breadth, and height, then the error in volume will reflect the combined effect of all three errors due to mathematical operations. Some common combination errors are error of a sum or a difference, error of a product or a quotient, or error in case of a measured quantity raised to a power. When two quantities are added or subtracted, the absolute error in the final result is the sum of the absolute errors in the individual quantities. If two physical quantities have their measured values A and B and mod delta A and mod delta B are their absolute errors, find the error delta C in the sum C is equal to A plus B. We have by addition C plus or minus delta C is equal to A plus or minus delta A plus B plus or minus delta B. The maximum possible error is C. Delta C is equal to delta A plus delta B. For the difference C is equal to A minus B, we have C plus or minus delta C is equal to A plus or minus delta A minus B plus or minus delta B, which is equal to A minus B plus or minus delta A plus or minus delta B, or delta C is equal to plus or minus delta A plus or minus delta B. The maximum value of the error delta C is again delta A plus delta B. When two quantities are multiplied or divided, the relative error in the result is the sum of the relative errors in the multipliers. Suppose a measurement Z is equal to A into B, and the measured values of A and B are A plus or minus delta A and B plus or minus delta B. Then Z plus or minus delta Z is equal to A plus or minus delta A multiplied by B plus or minus delta B, or Z plus or minus delta Z is equal to AB plus or minus B delta A plus or minus A delta B plus or minus delta A delta B. Dividing left-hand side by Z and right-hand side by AB, we get 1 plus or minus delta Z by Z is equal to 1 plus or minus delta A by A, plus or minus delta B by B, plus or minus delta A by A into delta B by B. Since delta A and delta B are small, we shall ignore their product. Hence, the maximum relative error delta Z by Z is equal to delta A by A plus delta B by B. This holds true for division as well. The relative error in a physical quantity raised to the power k is k times the relative error in the individual quantity. If z is equal to a square, then delta z by z is equal to delta a by a plus delta a by a is equal to 2 into delta a by a, Hence, the relative error in A square is twice the error in A. In general, if Z is equal to A to the power P into B to the power Q divided by C to the power R, then delta Z by Z is equal to P into delta A by A plus Q into delta B by B plus R into delta C by C. Whenever we measure the length or weight of an object, we note the measurement in the form of numbers. Here's a brick. Let's measure its length. Observe that the length is between 15.4 centimeters and 15.5 centimeters. Since we are not sure, we can say that the length is approximately 15.45 centimeters. In this measurement, 1 and 5 in the whole part and 4 in the decimal part are certain, while the 5 in the decimal part is uncertain. This 5 is uncertain because this is an approximate value. The values of many measurements in real life are decimal numbers. Digits in decimal numbers can be categorized as certain and uncertain. The number of digits in a measurement which are certain plus one additional digit which is uncertain are together known as significant figures. There are rules to determine the significant figures in a given number. The first rule says that in any measurement, all non-zero digits are significant. For example, we weighed a bar of steel that measures around 62.45 kilograms. Here, all the digits are non-zero numbers. In this number, all the 4 digits are significant figures. The second rule says that in any measurement, all the digits including zeros are significant for a decimal number greater than 1. Here, we have the length of a water hose, which measures 6.407 meters. This number is greater than 1. There are 4 significant figures in this number. The third rule says that in any measurement, if the decimal number lies between 0 and 1, the zeros to the right of the decimal point, but left to the first non-zero digit, are non-significant figures. Consider any number. Say 0.006452. Observe that there are 2 zeros between the decimal point and the first non-zero digit, that is, 6. These zeros are non-significant figures. Hence, the significant figures in this number are 6, 4, 5, and 2. Therefore, the number of significant figures is 4. The fourth rule states that if the measurement is a whole number, then the case becomes ambiguous if there are zeros to the left of an understood decimal point, but to the right of a non-zero digit. To remove this ambiguity, the number should be reported in scientific notation. That is, a into 10 raised to power b. For example, let's take a number 2507000. This is a whole number. According to rule number 1, there are 7 significant digits in this number. However, in this number, there is an understood decimal point, which is usually not written. The rightmost non-zero digit in the number is 7. There are 3 zeros between the 7 and the understood decimal point. We can report this in scientific notation as 2.507 into 10 raised to power 6. Now, the number of significant figures in this number is 4, since 2.507 is greater than 1. The fifth rule says that in any measurement, all the final zeros in a decimal number obtained by rounding off a decimal to a given number of decimal places are significant. For example, let's take the number 9.8982. There are 5 significant figures in this number. Let's round off the number to 2 decimal places. The resultant number 9.90 has the digit 0. But this number is greater than 1. Therefore, 0 is also a significant number. The number of significant figures in this number is 3. Using the rules we just studied, decimal numbers can be rounded off to the required significant figures. There are certain rules to round off the uncertain digits in a given number. The rule by convention says that the preceding digit is raised by 1 if the insignificant digit to be dropped is more than 5, and is unchanged if the latter is less than 5. Here is an example. We will round off 8.917 to 3 significant figures. This number has non-zero digits and there are 4 significant figures. In the decimal place, we will round off 7, resulting in the number 8.92. Here is another example. Round off 7.9342 to 4 significant figures. This number has non-zero digits and there are 5 significant figures. In the decimal place, we will round off 2, resulting in the number 7.934 as the number to be dropped, which is 2 is less than 5. Now, consider 2 numbers 3.945 and 3.975. Let us round them off to 3 significant digits. In this case, the insignificant digit to be dropped is neither greater than nor less than, but is equal to 5 in both the given numbers. To do this, we have another convention, which states that if the preceding digit is even, the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 1. Thus, the answers are 3.94 and 3.98 for the rounded off numbers as shown. Here, the length can be written as 8.1 plus or minus 0.1 or 8.1 plus or minus 1.2%. And the breadth can be written as 5.1 plus or minus 0.1 or 5.1 plus or minus 2%. Hence, using the combination of errors rule, the area of the field calculated as the product of these two quantities would be 41.31 plus or minus 3.2% or 41.31 plus or minus 1.3 square meters. We can report this as 41 plus or minus 1 meter square. Here, 1 square meter is the error in the result. Thus, the result also has two significant digits, which is same as the original data. Rule number 2 says that the relative error of a value of a number specified to significant figures depends not only on n but also on the number itself. If there are two quantities, say 10.01 meters and 80.5 meters, both carrying an error of 0.1 meter, then the relative error in 10.01 meters is plus or minus 1%, while the same for 80.5 meters is 0.12%. Another important point to remember with significant figures is that intermediate results in a multi-step calculation should be taken to an additional significant figure in every measurement than the number of digits in the least precise measurement. Consider a number, say 6.55. The reciprocal of 6.55 taken to the same number of significant digits, that is 3, is 0.152. However, the reciprocal of 0.152 is 6.58, which does not match the original data we had. Now, if we consider the reciprocal of 6.55 to 4 significant digits, we get 0.1527. The reciprocal of 0.1527 taken to 3 significant digits is equal to 6.55, which is the original data again. We learnt earlier about different physical quantities, of which 7 are considered fundamental according to the SI system of measurements, while the others are derived physical quantities. The 7 fundamental quantities are length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. These are also referred to as base quantities. All other physical quantities can be conveniently derived from these base quantities. Thus, we have relationships between fundamental quantities and derived quantities. Therefore, when a derived quantity is expressed in terms of base quantities, the resultant expression is the product of different powers of the base quantities. For example, consider the quantity force. Force is product of mass and acceleration. Mass is a base quantity, and acceleration is the derived quantity, which is the ratio of change in velocity to time. Velocity which is also a derived quantity, is the ratio of displacement to time. Displacement, in basic terms, is length. Thus, velocity can be expressed as the ratio of length to time. Using the same logic, we can write acceleration as length by time divided by time. Thus, the expression for a quantity force can be simplified as shown. From the expression, it is clear that the exponents of mass, length, and time in the expression for force are 1, 1, and -2 respectively. These exponents of base quantities in the expression for force are called dimensions. Thus, the dimensions of a physical quantity are the powers or the exponents to which the base quantities are raised to represent that quantity. We say the dimensions of force are 1 in mass, 1 in length, and -2 in time. For convenience, we use symbols to represent base quantities as follows. For mass, we use m. Length is denoted by L and time by T. The other four base quantities are represented by symbols of their SI units, namely electric current by I, thermodynamic temperature by K, amount of substance by mole, and luminous intensity by CD. The physical quantity expressed in terms of its base quantities is enclosed in square brackets to show that it is an equation among the dimensions of the quantity and not among the magnitudes. Thus we can write the expression for force as force is equal to mLT power -2 as shown. Such an expression for a physical quantity in terms of its base quantities is called its dimensional formula. An equation which equates the quantity with its dimensional formula is called a dimensional equation. Of the 7 base quantities in the SI system, we see that only 3, namely mass, length, and time, exist in the dimensional formula for force. Thus, we can say that the dimensions of all the other 4 base quantities in the expression for force are equal to 0. In mechanics, most derived quantities are related to only the 3 base quantities of the 7, namely mass, length, and time. Let us look at another example. Let us find the dimensional formula for pressure, which is equal to force per unit area. Area is the product of length and breadth. Length and breadth represent the base quantity, length. Thus, area can be expressed as length square, and hence its dimensional formula is L power 2. We know that the dimensional formula of force is mLT power minus 2. Now, the dimensional formula of pressure is obtained as shown. Following the same methodology, we find the dimensional formula for the volume of a body. Volume is the product of length, breadth and height. Height also represents the base quantity length. Thus, the dimensional formula of volume is L power 3. Similarly, we can find the dimensional formula of mass density, which is the ratio of mass to volume. The dimensional formula for density is ml power minus 3. So far, we have discussed derived physical quantities, namely force, pressure, and density. These quantities have units, namely Newton, Pascal, and kilogram per meter cube, respectively. But there are certain derived physical quantities that do not have units. For example, relative density is the ratio of the density of a substance to the density of water. As it is the ratio of two identical quantities, it does not have any unit. Therefore, the quantity relative density does not have any dimensional formula. Another example is absolute refractive index, mu, of an optical medium, which is the ratio of the speed of light in air or a vacuum to the velocity of light in the given medium. Refractive index is just a number and is significant even though it does not have any unit, because the value of mu of a medium indicates the extent to which a ray of light bends on entering the medium at a given angle of incidence. Refractive index of a given medium is constant and does not have any dimensional formula. You will learn about refractive index in detail later in the course. We also have certain physical constants, each of which has a unit as well as dimensional formula. For example, the universal gravitational constant G is a constant whose value is 6.67 into 10 power minus 11 Newton meter square per kg square and is denoted by the expression G is equal to force F into distance d square by mass m square. Thus, the dimensional formula of G is obtained as shown. We obtain the dimensional formula of G as m power minus 1 L power 3 T power minus 2. You will learn about G in detail later in the course. So far, we have discussed physical quantities which are expressed as the product of base or other derived quantities. We also learnt that a dimensional equation is the equation among the dimensions of the quantity and not among the magnitudes. But we may encounter situations where we need to add or subtract different terms involving base quantities. It is very important to know that when we write L plus L, as shown, we mean length added to length. So, we get length. Again, it is not 2 times L as we are not adding the magnitudes of the length. Similarly, if velocity is subtracted from velocity, we get velocity. Thus, Lt power minus 1 minus Lt power minus 1 equals Lt power minus 1. The table shows the list of some of the physical quantities and their dimensional formulae. You will learn about the applications of dimensional formula later in the course. We learnt earlier about the dimensions of some physical quantities. The dimensions of a physical quantity are the powers or the exponents to which the base quantities are raised to represent that quantity. An expression for a physical quantity in terms of its base quantities is called the dimensional formula. An equation which equates the quantity with its dimensional formula is called the dimensional equation. We will now learn about the uses of these dimensional formulae and dimensional equations. We know that a dimensional equation is the equation among the dimensions of a quantity and not among the magnitudes. Thus, when we write L plus L, as shown, we mean length added to length. So we get length again. It is not 2 times L as we are not adding the magnitudes of the length. This property of a dimensional equation can be used to check the dimensional consistency of equations by analyzing the dimensional formula of quantities on both sides of the equation. For example, consider the motion of a body moving with an initial velocity u and uniform acceleration a, having made a displacement s in a time interval t. The motion of the body can be represented by the equation s is equal to ut plus half at square. Let us now verify the consistency of this equation using dimensional analysis. On the left-hand side of the equation, we have displacement s. This is basically length and its dimensional formula is L. On the right-hand side of the equation, we have 2 terms, each involving the product of 2 different quantities. The first is ut and the second is half at square. When the magnitudes of 2 or more physical quantities are multiplied, their dimensions are also treated in the same manner as done with ordinary algebraic symbols. In this case, in the first term, it is the product of velocity and time. The product of the dimensions of these quantities is Lt power minus 1 into t, as shown. On simplification, we get L. The second term on the right-hand side of the equation is half at square. Half is a constant and thus does not have any dimensions. In the first term, it is the product of acceleration and time square. The dimensions of A are LT power minus 2 and that of T are T. Thus, the dimensions of AT square are as shown. Taking the dimensional formula of the physical quantities in both the terms on the right-hand side of the equation, substituting their corresponding dimensions and simplifying, we find it is equal to L, which is the dimension of length as obtained on the left-hand side of the equation. Thus, the dimensions of the quantities on both sides of a given equation are the same. This proves that the equation is correct. It is very important to note that physical quantities represented by symbols on both sides of a mathematical equation must have the same dimensions. This principle is called the principle of homogeneity of dimensions and is useful in checking the accuracy of an equation. This principle can also be used to derive expressions for physical quantities if the other quantities on which it depends are mentioned. For example, we can derive an expression for the time period of a simple pendulum, assuming that its time period t depends on the length, mass of the pendulum, and the acceleration due to gravity at a given place. Let us take the constant of proportionality k as 2 pi. We assume that the time period is proportional to L power A, M power B, and G power C, where A, B, and C are constants. Replacing the proportionality symbol, we get a constant k. Hence, the time period is equal to k into L power A, M power B, G power C. We now need to find the values of A and B using dimensions of the physical quantities on both sides of the equation. The dimensional formula for time is T. The dimensional formula for length is L. The dimensional formula for mass is M. The dimensional formula for acceleration due to gravity is LT power minus 2. The constant does not have any dimensions. Hence, the dimensional formula of the quantities on the right side of the equation is simplified as shown. Let this be equation 1. The dimensional formula of the quantity on the left side of the equation is as shown. As we do not have the term for M and L on the left-hand side of the equation, we take their powers to be 0 as shown. Let this be equation 2. Equating equations 1 and 2. We compare the powers of the base quantities on both sides of the equation. Thus, we get B equal to 0, A plus C equal to 0, and minus 2C equal to 1. On simplification, we get the values of B equal to 0, C equal to minus half, and A equal to plus half. Thus, the expression for the time period of the simple pendulum becomes 2 pi into the square root of L by G as shown. The value of k, which is equal to 2 pi, cannot be found by using dimensional analysis. However, this method cannot be applied to derive equations where addition or subtraction of different terms is involved. For example, we cannot derive the equation S is equal to ut plus half at square using dimensional analysis even though we checked its dimensional consistency. Dimensional equations can be used to convert units of a given physical quantity from one system to another and to thus find the conversion factor. For example, consider the physical quantity force. The dimensional formula of force is mLT power minus 2. The SI system of unit of force is Newton, and its CGS unit is dyne. Hence, 1 Newton is equal to 1 kilogram into 1 meter into 1 second power minus 2. Similarly, 1 dyne is equal to 1 gram into 1 centimeter into 1 second power minus 2. Now, we divide 1 Newton by 1 dyne and then find the ratio of Newton to dyne as shown. Thus, 10 power 5 is the conversion factor to convert Newton to dyne. Dimensions are generally used as a basic test to check the consistency of an equation, where there is a doubt regarding its correctness. However, this test cannot be completely relied upon, especially in the case of dimensionless quantities or functions. Dimensionless constants cannot be obtained by this method. For example, the arguments of some dimensionless functions such as trigonometric, logarithmic, and exponential functions cannot be obtained using dimensional analysis. The ratio of similar quantities results in a pure number, which is again dimensionless. For example, angle is the ratio of arc length to radius, which is length divided by length. Absolute refractive index of a medium is the ratio of the speed of light in a vacuum to that in a given medium, which is the ratio of speed to speed. The test of consistency of dimensions not only tells us the consistency of units, but also helps the user ignore the units to be mentioned and conversions among multiples and submultiples of units. If an equation is put to the consistency test using dimensional analysis, and if the equation fails, it means that the equation is proved incorrect. If the equation passes the consistency test, it does not mean that the equation is correct. Thus, an equation proved to be dimensionally correct need not be an exact equation, but an equation that is proved to be wrong dimensionally must be a wrong equation. The dimensional analysis method is very useful in drawing relationships between various interdependent physical quantities. This analysis can only test dimensional validity, but not the exact relationship between the physical quantities in any given equation. The dimensional method cannot differentiate between physical quantities which have the same dimensions. For example, even though the quantities energy and torque have the same dimensions, they are completely different in every sense.